385 million years ago, the land was all but empty. The continents were home to only some sparse plants and fungi and a few pioneering arthropods. Life in the oceans, however, was booming. The waters teemed with squid, bony fish, and sea scorpions. But there was one group of fish that was about to go its own way. In time, these enterprising fish would undertake one of the most important journeys in the history of life. They'd follow in the footsteps of the arthropods to become the first vertebrates to live on dry ground. But they couldn't just move on to land. Not yet. First, they had to acquire the ability to breathe air. The giant link between fish that breathe through water and fish that breathed air has been really hard for us to study and understand. That's partly because the organs that did the work of breathing, either gills or lungs, don't fossilize well. But it's also because until pretty recently, there just haven't been a lot of fossils from that time for us to study. Fish began their transition onto land about 400 million years ago, during the Devonian period. And for a long time, one of the few fossils that experts had to work with was a fish named Eustinopteron, originally found in Quebec in the 1880s. It lived in shallow, estuary waters around 380 million years ago, and like the famous coelacanth, it was a lobe-finned fish. Instead of having long, delicate fins with lots of joints in them, like you'd see in a goldfish, its fins were shorter and stronger. These hardy limbs could have helped Eustinopteron move itself along in the shallows as it hunted other fish, but its fins probably weren't strong enough to let it walk on land. Another major find came about in the 1930s, when scientists uncovered Ichthyostega, a meter-long creature found in rocks in Greenland dating back 364 million years. Ichthyostega had a body that was a lot more salamander-like, including a fully developed pelvis, strong limbs, and even fingers. But Ichthyostega still probably dragged itself around with its front legs, a bit like how a mud skipper moves today. And it also had a thick paddle-like tail for swimming, which means it likely spent a lot of its time in the water. But perhaps neither of these fossils is as key to this story as Tiktaalik, a 375 million year old animal found on Ellesmere Island, Canada in 2006. Tiktaalik had a fishy body, but a head like a salamander's and stiff leg-like fins that could have supported its weight outside of the water. And most importantly, it also had bigger primitive hips, so its hind limbs had something to anchor onto, an important step in becoming a fully four-legged animal. However, Tiktaalik's travels on land were probably still stuck in front-wheel drive. Even though its legs and hips were bigger than Eustinopteron's, they weren't strong enough to bear the strain of walking on land. With traits that seem halfway between a fish like Eustinopteron and a four-legged animal like Ichthyostega, Tiktaalik is a textbook example of a transitional fossil from this time. And despite their differences, all three of these fossils are considered to be tetrapodomorphs, a group that includes early four-footed animals and the lobe-finned fish that are closely related to them. Now, one big trick to living on land, of course, is breathing. So how did these animals, which had been adapted for millennia to life underwater, start to breathe air? Well, we know that all three of our friends, Eustinopteron, Tiktaalik, and Ichthyostega, had gills. Because even though gills themselves don't fossilize very well, the bony arches that support the gills do, and each of these animals had gill arches. But even though they still had gills, that doesn't mean they couldn't breathe air. It turns out the most important clue for when fish started breathing air isn't the absence of gills. Instead, it's the shape and location of a little hole in the skull. This hole can still be found in many fish today. It's the opening of a tube called the spiracular tract that's used to bring water in towards the gills. This feature is really handy because it allows fish to breathe when their mouths are busy eating. And this little skull hole can tell us a lot about when tetrapodomorphs first became able to breathe air. All you have to do is compare where it shows up in the fossils with where it appears in different kinds of modern fish. Now, in most modern fish, the opening of the tract appears on the sides of the face, near the front of the skull, which puts it pretty much right on top of the gills. But there are also fish today that breathe air, and in one of these fish, the bichir from Africa, the hole is bigger and sits on the top of its skull, farther back, kind of like a blowhole. What's more, the opening also sits at an angle, not straight up and down. That's an important clue because this angle creates a more direct path for air to travel to the bichir's lungs. Now compare all of that with the skull openings in tetrapodomorphs. In Eustinopteron, the spiracular tract opens up near the front of the skull, just like in most water-breathing fish with gills. But the hole is on the top of the skull, not the side. In this way, it kind of resembles the bichir, which uses its head hole to breathe air from the surface of the water. So Eustinopteron was maybe breathing air in addition to water, and since the hole was close to the front of the face, they probably used their gills to handle both. But in both Ichthyostega and Tiktaalik, that hole is much bigger, is closer to the back of the skull, and sits at an angle, just like it does in the bichir. This means the tract in these ancient animals was pointing right to where a primitive set of lungs would have been. It's not the clear-cut evidence that a nice set of fossilized lungs would be, but having a larger passageway that sits closer to where the lungs are in today's lunged fish is a good sign that both Tiktaalik and Ichthyostega had some sort of primitive lungs. As for where these lungs came from, experts think they derived from an organ that many modern fish still have today, a swim bladder. Swim bladders are often filled with air, which fish gulp down to help keep them buoyant, and ancestors of Tiktaalik and Ichthyostega probably had them. The thinking is that among some lobe-finned fish, the swim bladder became bigger and contained more blood vessels, so it became better at putting oxygen into the bloodstream. In time, this organ took on a different function, finding a new use for the air that was already there: breathing. This kind of makes sense. If you look at air-breathing fish today, like the lungfish and the bichir, their swim bladders are split into two and so full of blood vessels that they look basically just like our lungs do. But why would any fish, modern or fossil, bother with breathing air when there's all that lovely water around? Well, during the Devonian, things were complicated, and all of those complications led to a steady drop in the amount of oxygen in the oceans. On land, new plant species were diversifying, which you'd think would be good for oxygen levels, except all of those new plants were also dying on land, and then getting washed into the ocean. All of that organic material fueled huge blooms of algae, and then bacteria, which in turn sucked up oxygen from the ocean. So by the late Devonian, right when fish started to transition onto land, oxygen in the air was really low. Some estimates go as low as 13%, compared to almost 21% today. For animals, low oxygen is generally bad, but for organisms that live in the water, it's even worse, because oxygen concentrations are always lower in the water than they are in the air. So when oxygen levels first started to fall 385 million years ago, the benefit of transitioning onto land was pretty clear: no more gasping for breath in the water. Being able to breathe air made Tiktaalik, Ichthyostega, and maybe even Eustinopteron more energetic and better able to hunt their food. And these first air breathers eventually gave rise to the true tetrapods, the first vertebrates to live on dry land full time. Eventually they lost their gills, and by the time the Devonian period had ended and the Carboniferous was underway, they had also lost their spiracular tracts and started using a totally different kind of skull hole for breathing, called nostrils. But those lobe-finned fish that were our ancestors weren't the only fish that figured out how to breathe air. Today there are lungfish, mudskippers, bowfin, and bichir. They're not direct descendants of the likes of Tiktaalik. Instead, they each acquired the ability independently at different times. It just goes to show you that breathing air has turned out to be very convenient for a lot of us over time. So remember, for all the breaths that you're taking today and the way that you're taking them, you owe your fishy ancestors a debt of thanks. Thanks for joining me today, and I have big news! Eons is now on Patreon! Patreon is a voluntary subscription service that helps us keep these videos coming. So if you'd like to support the show, head over to patreon.com/eons and sign up at any level you want. Now let me know what you want to learn about. Leave me a comment down below, and if you haven't already, go to youtube.com/eons and subscribe.